All right, so today I'm going to be talking about Hermes, which is a multi-tiered IO buffer system. It's a project in collaboration with the HDF group and the Gnosis Research Center. So storage hardware has become very complex. Many different types of hardware have emerged and are currently emerging. It started out with the hard drive, and now it's all gone all the way down to the Compute Express devices, which are starting to find some of their way into machines. A lot of machines are integrating several of these different technologies all at once. El Capitan, for example, integrates NVMe in addition to hard drives, and the Aurora machine includes pretty much all of these except CXL. However, having all of these different types of storage, even though they all have great characteristics, each of them, deciding where to put your data is a very difficult challenge. First and foremost, a lot of scientific programs use HDF5 as their IO buffering system, but HDF5 does not natively support IO buffering. So it's pretty much entirely up to the users to decide where that data actually goes. Domain scientists are not IO experts by any means. There's a lot of work out there trying to automate IO parameters, trying to make it so scientists don't really have to think about it. And a lot of these are just configuring the HDF library itself, not integrating it into all of that mix. This leads to poor data placement decisions made by the scientists. Typically, the de facto standard is just ignore the local storage device that's the data on the DFS. Lawrence Livermore, for example, has extremely low resource utilization of their NVMe's. Tiered IO must become simpler. We need to remove the responsibility of tiered storage from these users. We must intelligently decide where to place data based on device application characteristics. We need to be able to correct the placement of data dynamically to adapt to changing application behaviors, and we need to support a variety of applications without requiring code changes. So to solve these different challenges, we propose Hermes. So in order to address intelligent placement decisions, Hermes provides automatic data placement engines. So you don't have to think about where the data actually is, you just put your data into Hermes and then data is set. After the data is in place into Hermes, we have a dynamic buffer organization policy, which allows you to correct the placement of data dynamically. A lot of applications, their patterns change throughout the program, and having static policies that just place the data is not enough. Lastly, we provide several adapters to support a variety of applications without requiring code changes. So Hermes is a multi-million-dollar NSF project between the HDF group and the Center. We released Hermes version 1.2. It's available. It's in the HDF group's public repo. It is usable. You're welcome to try it. This talk is going to discuss the core design of Hermes, some of the recent features, and various use cases. So, the general use case of Hermes is that Hermes is deployed within the context of an HPC job. You launch Hermes, then you launch your application, and your application puts data into it. Applications can only buffer data in Hermes during the job. HPC sites are limited. We can't simply deploy Hermes like a parallel file system. So we're constrained to making it so that Hermes lives within the lifetime of the job. While the application is placing data into Hermes, we asynchronously flush that data to the parallel file system so that data remains alive after the program terminates and after the job terminates. At the end of the program, since we're placing data into these faster tiers, we should be able to have a significantly faster performance since that data is being flushed down asynchronously and not on the critical path of the program. So in order to interact with Hermes, applications can use the Hermes native API. Hermes has two primary data types, a blob, which is an array of bytes, and a bucket, which is a named collection of blobs. The API that we have is analogous to a key value store. The two main APIs we provide are put blob and get blob. To put these two abstractions into perspective, below is an example. So this example is a case where we have the USDA nutrition data set. In this case, we make the entire data set a bucket, and each row of this data set is a blob. So for example, we have the key being butter, and then if you query Hermes, you do get blob of butter, it's going to return this tuple containing the calories, fat, the carbs of this entry. This is not the only way that Hermes can represent this case. There are many different ways you can build a key value store. You can make it column-wise, for example, or you can make it partial. You can have several rows in a single blob. It doesn't need to be this simple. But for the sake of understanding, this is how we can explain the difference between a blob and a bucket. So outside of the native API, Hermes has several adapters. These adapters make it so that you do not have to change your application in order to use Hermes. The native API would require you to make changes, but Hermes has several other APIs that it supports, including POSIX, several API implementations, the HDF5 library, and Gnosis, which is a work in progress. The general idea is that these interceptors or adapters convert the I/O requests of the application into a native Hermes API call. So the Hermes library is a thin. It doesn't do much. Essentially, it takes different APIs and it converts them into messages. And it sends these messages to the Hermes runtime, which is where they're actually executed. The messages are sent through a high-performance shared memory queue system, so it's not a huge performance drag there. There are two main benefits to this design of separating Hermes from the application. So first, Hermes can run longer than a single application. If you have several applications running in a single job, if you had Hermes tethered to the application itself, you would have to flush the data every time an application closes. With this approach, you get the benefit of having the data across the applications. And secondly, you can have multiple applications using Hermes simultaneously. While this isn't necessarily typical in HPC sites, a lot of other situations like cloud systems would be able to benefit from this approach. So after you convert the I/O requests into these messages, the first typical message that you would send is a put. So when you call a put, it goes to the data placement engine, and the data placement engine decides where to put the blob in the distributed memory and storage hierarchy, the DMSH. There are three algorithms that we have currently. There's the minimize I/O time, which simply places the data in the fastest available space. There's the round robin policy, which does pretty much what you think it does. It just round robins across the tiers, and it gets an equal distribution of the blobs across the tiers. And then the random one also does pretty much what you think it does. It uniformly randomly chooses the tier to place it. So to demonstrate the impact of these different tiering policies, we'll run a simple example. So in this case, we run two workloads, VPIC, which is a simulation for modeling kinetic plasmas. It's a write-heavy simulation. It's a write-only simulation that just produces a bunch of data. And then BDCATS, which is a particle clustering algorithm, which takes the input of VPIC and performs clustering to identify spatial units. So we ran this evaluation with 16 nodes and 16 processes per node, and we used the minimize I/O time DPE. Overall, we see that with each additional tier, Hermes performs significantly better. So this demonstrates that the DPEs that we provide can efficiently abstract these different tiers away from the programmer and make it so you don't really have to think about where the data actually goes. You can use these algorithms to just let the data be wherever it's going to be. Now, we have 3 different DPEs. So there are pros and cons to each of them. Round robin and random sound weaker than the minimized I/O time from the figures you saw, because the minimized I/O time performed the best. But the real difference is that they have different resource utilizations. So if you don't want to waste all of your memory, you might want to use a random engine or the round robin engine, or maybe you want to make an entirely new one. The set of data placement engines is completely extensible. You're not limited to the 3 policies that have been currently defined. After the data placement engine is called, you created your blob or your buckets, and now you have to store that metadata somewhere. So the metadata manager essentially is responsible for just holding basic information about the blobs and buckets. It contains the position of the blob in the distributed memory storage hierarchy, and it can also be configured to track blob and bucket operations. So one use case for this is monitoring. If you track the order with which the blobs are created and modified, that allows you to make more interesting decisions in things like prefetchers and the data placement engine. After the metadata manager is the buffer organizer. So at this point, the data has been placed in storage. So the data placement engine has been called, and you're placing the data in storage. So the buffer organizer is primarily responsible for correcting the position of a blob after it has been initially placed. So there are several factors that are involved in making this decision. I'm not going to recite the entire algorithm to you, but I'll say the factors that are involved. The first main factor is I/O size. If you have a small amount of I/O, like a 4 kilobyte I/O, you might not want to migrate it quickly because it doesn't take up that much space anyway. Why waste your time? The second is access frequency. This is the amount of time that a blob has been accessed. So that's a pretty obvious one. If you're accessing a blob a bunch of times in a time frame, you probably want to keep it in a higher tier of storage. And access recency, which is how recently this was accessed. There are plenty of applications out there that exhibits recency. If you access something recently, you might access it again in the near future. So in this case, you might want the score to be a little bit higher. And lastly, our user base. So the user might have data that they know the kind of data it is. Metadata, for instance, will probably do the same. Otherwise, every time you want to look up the position of a key in a table, you'll have to go through this, and that would be a huge performance drag. So the buffer organizer provides you a lot of flexibility with how to decide where the blobs live over time, and not just initially. To demonstrate a little bit how this works, this on the left is an example of how the buffer organizer handles workloads with phases. So here we have initially a compute phase, which, for example, produces a bunch of particles, and then in the I/O phase, it persists all of those particles, and then another compute phase starts. During that compute phase, you're not performing I/O, so you have a bunch of time to actually move this data down to a lower tier of storage and make room for new data to come in. So the next thing after the data placement engine, so the reverse of the DPE is the prefetcher. The DPE writes data, the prefetcher sucks it. The idea is that the prefetcher changes the storing of the blob in the buffer organizer based on a predicted access time. So let's say you have a sequential algorithm. The sequential algorithm is pretty simple. All you have to do is go to the next thing in the list. So you go to the next thing in the list or the next 5 things in the list, and you make those scores really high. And then when that time comes where you actually need that data, it's already where you want it to be. So the prefetcher, the sequential algorithm is fairly simple. However, we've made it so that you can develop more interesting algorithms. We made it so that the prefetchers can be defined entirely in Python, so you don't have to be limited to C++'s clunky machine learning libraries. You can build your prefetchers using fancy Python, regression learning, at least long-term, short-term memory models, all of those sorts of things, and that could give you essentially an OR that allows you to know when data actually needs to be where it is. And then lastly, we'll talk about the I/O clients. The I/O clients are pretty simple. Essentially, each different storage device has many different APIs that they can expose. Everyone exposes POSIX, but there are more nuanced APIs that can give you more performance. The SPDK, for example, was developed by Intel, and it gives you significantly better latencies to NVMe than the POSIX API does. Light NVM is a similar kind of category to the SPDK, except in addition to this asynchronous kind of behavior the SPDK gives you, it also allows you to program the flash translation layers on the NVMEs. So you can build completely customized garbage collection algorithms and get some major performance benefits there. And lastly is the memory map for persistent memory and the upcoming compute expressing devices. Essentially the idea of the I/O clients is that it takes all of these different APIs and it presents them as a single unified interface. Abstraction always has complications, but in this case, the buffer organizer needs something unified in order to actually put data in. The API that's exposed is slightly more complicated than a block device interface. But yeah. So now that we've talked about the core design of Hermes, the core features of Hermes, I'll talk about some of the additions that we've made to the Hermes API. So recently we made it so that Hermes allows you to make composable storage sets. So in the past, Hermes just, you put the data in and that's the end of the day. However, there are several applications that demand more out of storage sets, simply putting the data. On the left is an example of a pipeline where you first put the data into Hermes and then it applies compression and encryption before it goes to the data placement engine. A typical example of this would be compression oftentimes is used for performance, but in this case it's used for data reduction simply pure and max, because why would you need performance if you're doing encryption? This is more about security and making sure that your tape archives don't get overloaded. Secondly is an archive or a pipeline where you put data in and then you transparently derive quantities. So this example is you put the data in and then you perform some calculus, for example, an integral. We've had some people come to us in recent PI meetings that said that we wanted to have the ability to take the integral of data after it's been put into HDF5. So with this composable design, you can design your calculus operator, plug it in, and then get that transparent database without having to do a bunch of data copies, data reorganizations, all those sorts of things. And then lastly is a class where you perform analysis live. So an example of this is you put the data, you perform clustering on the data, and then you place the data. A typical example of transparent clustering would be credit fraud detection. A lot of banks need to use K-means, for example, to identify patterns in banking data sets so that they know when to send you an email if someone's using credit. Next, we'll talk about Hermes for the cloud. Hermes was originally conceived to be HPC focused, but we've extended the design a little bit so that it can be used for more than just HPC. It's also compatible with cloud. A lot of cloud applications can be built on top of the API that Hermes exposes. Earlier in the presentation, you mentioned key value stores. And other examples would be databases, graph stores, those kinds of things can be implemented on top of this. What's my time is running a little bit short. So we'll describe a quick evaluation we did of Hermes for some cloud workloads. So the Yahoo Cloud Service benchmark is a benchmark widely used by these kinds of systems in the cloud. It compares various web workloads, that are typical in web applications. Typically, these programs are latency sensitive. As you can see from the chart below, each of these workloads perform I/O in the unit of 1 kilobyte. HPC, you see more like 1 megabyte. This is 1,000 times smaller. This really stresses the software overheads of the storage stack in Hermes. We compared against Redis, which is widely used in cloud for doing pretty much what it sounds like, storing keys. Hermes and Redis have analogous APIs, so it makes them very easy to compare against one another. So the 5 workloads we ran were A through F. I skipped E, but A, as you can see, A is half read, half write. B is mostly read. Most of the other workloads are read. The only one that's not read heavy is the first one and the last one, where it's 50-50. So in these cases, Hermes performs 2 to 3 times faster in each case. And the reason is because Redis requires several data copies to actually get data to the Redis daemon. First, it serializes the data, then it copies it to a buffer, and then it copies it over to the Redis runtime. It's a fairly expensive process. So in order to reduce these kinds of things, Hermes uses shared memory. Data primarily goes into shared memory, so you don't have to incur all of these data copies on the live path. And this results in the significantly improved performance that you see in these graphs. In addition, writes and runs are completely asynchronous, so you don't have to wait for the writes to actually complete. Writes tend to be very expensive compared to reads because you have to update all of those metadata indexes. But in the case of Hermes, we make the use of queuing to maintain strong consistency while also being able to be completely asynchronous for the writes. Okay, so we demonstrated that Hermes can yield as much as 15 times performance boost for applications by leveraging tiering. We showed that Hermes can be adapted to a wide variety of applications spanning an HPC and cloud, and we described various use cases that can benefit from a tiered active storage that Hermes currently provides. As a quick aside, some of the future work, we didn't talk much about deep learning in this presentation, but one of the future works that we're looking into is running various AI workloads over her. Okay, thank you.
Any quick questions?
Given applications using mainly just using handle transferring the memory to the CPU memory, or?
That's a good question. Currently, no. This is a project that we're also working on, making it so that Hermes can buffer data in GPU memory and to make it so that tensor operators executing on a GPU put data into Hermes and making it one cohesive system that works across accelerators.
It's an ongoing project. We're looking into optimizing LLM stack items with Hermes by a lot of, when he showed the IO clients, it's very easy for Hermes has a factory for IO clients, so we extended that for NVMe.
Oh, yeah. Or rephrase a little bit.
Yeah. So we're looking into this. We're working on it to optimize IO, machine learning workloads with Hermes by presenting the IO activities of Hermes. Also, maybe working to a GPU IO client. So, like we showed the HDD client of memory client have partially working GPU IO client. Hopefully, in the next 3 to 4 months, we will have that ready prepared for everyone to use.
Cool. There's one question in the Google Docs. It's what benefit could Hermes obtain if it weren't limited to the lifetime of the job?
The nice thing would be workflow optimizations, because right now a lot of workloads They share the data between phases. Some of my coworkers have written papers on discussing how workflow phases actually share data between them. So it's difficult to implement that with the limitations right now.
Okay. I have a few more questions, but I will talk to you later in the interest of time. We can move on to the next one. Let's thank the speaker again.